There we go. How's it going? Can you all hear me today? Cool. Excellent. Everyone have a good weekend? Have a safe Halloween, hopefully, like no virus spreading, but still fun, hopefully. That's good. It was good. Guess it's kind of hard to find things to do when you can't go anywhere. I mean, to think this was the first full moon on Halloween on a Saturday in like 70 something years, and the pandemic kept us all at home. It's just not fair. Also, there might be a cat photo bomb today. She's sleeping right off screen. So apologies in advance for that. All right, cool. So it is 2 o'clock now. So let's get started. I'm sure people will be trickling in. I guess by virtue of the fact that you are here, it means that you correctly changed your clock. If you know anyone who didn't, well, hopefully they'll figure it out before lecture is over. But as always, like even if you do miss something, I put the slides up after class, and I will put the video up after class as well. So even if you find yourself zoning out, because it might start getting dark before our class is over, I guess maybe not at 3:15, but that'll be there in case you kind of zone out. But anyway, so today we're going to talk about streams, about rivers and creeks and flowing things and the floods that they cause. But before we get into that, just does anyone have any questions, concerns, comments, etc. Before that? Just logistical confusion, etc. Okay. Whoops. Whoops. No. Okay, so if any, as always, if you do think of something, just don't hesitate to say it or put it in the chat box. But yeah, so this week is our last week of lectures before the next test. So I know it feels like time is extremely nonlinear in 2020, which is kind of true. But our next test is coming up 1 week from today. And so like all of the others, it's going to be exactly like the others in format. We're going to meet in here for like 25 minutes first to do a review. And then you'll have 45 minutes to do 30 multiple choice questions. And it'll be all of the sedimentary rock stuff, then all of the 3 lectures of sedimentary rock stuff, the lecture of mass movements, then today's stuff about flowing water, and this coming Wednesday stuff about glaciers. So those are all the things that you have to worry about for this test. Definitely, you know, I would say go through those study guides and sort of go through each point and go, yeah, can I describe that? Can I explain that? Etc. Just sort of quiz yourself that way. You can look back at the quick quizzes as always, and it'll explain sort of if you got it wrong, why that answer was wrong, and usually if you got it right, why that answer is right. So you can use those to study as well. And also there's one more chance for office hours before the test. So again, tomorrow from 2 to 4, if you're not too distracted by other things happening tomorrow, or if you would like a distraction from doom scrolling, you're welcome, you know, to just stop by office hours and ask me anything. And also don't forget that the extra credit is due the week after the test. So Wednesday the 11th is Veterans Day, and we don't have class on that day. So that's kind of what we're looking at. But any questions, concerns, things about that right at this point? All right, then let's get going. Let's talk about flowing water. I figured for my background today, I should go with a nice autumnal looking river. That's Shenandoah National Park in Virginia. Just because it's fall, it's gonna get dark, and yeah, it's still 90 degrees, but we can pretend. So yeah, let's talk about streams. So in general, when I say the word stream, like how much water do you think I'm talking about? Like not much, yeah. So that's a pretty common sort of vernacular thing, yeah. So hold on. So a stream, a lot of people think of it as not much water, but from a geology standpoint, and from the standpoint of how we're going to talk about it in this class, a stream is actually any body of flowing water that flows through a channel. So it can be just a little bitty thing, like the colloquial thought of what a stream is, or technically, by this definition, even the Mississippi River is a stream. It's just a really big sucker. Mississippi meaning literally big river. Yeah, so a river, like colloquially, you would still, you know, want to use river to say something bigger. But some of it's also regional. Like again, for this background, I mean, the Shenandoah as a river is big, but like so there's some things in Virginia that they would call a creek that is larger than a lot of rivers in California, and a lot of that has to do with the climate and how much water there is. But no matter what, it's that definition here. No matter anywhere in the world, is that a stream is a body of water that runs through a channel. So in this context, what's a channel? Like not a YouTube channel.
Like a trench?
Yeah, like a trench or a ditch or just an indentation that water flows in. And so one that we, whoops, oh, I switched the order of these slides. But one that we see all the time here is this one, perhaps. The LA River is obviously somewhat artificially or extremely artificially enhanced, as it were. But in this case, it's a really nice diagram of sort of what an idealized, simplified river or stream structure is. So in this case, the central channel is where most of the water is most of the time. And it's a deep like trench indentation row thing that the water is in. And so if you've got a channel and water is flowing in it, you've got a stream. Or as it turns out, which we'll get to in that other slide, sometimes if you've got a channel but water isn't in it all the time, it's still a stream. But an idealized stream is, again, that channel in the middle, and then you'll have what's called a floodplain on either side of it. So here, I mean, on the LA River, it's concrete. In a natural river, it would be a lot of sediment of different sizes, depending on how fast that river is flowing. We'll talk about that later today. Usually it's a lot of softer, like smaller grain stuff, but there can be some big stuff. And then at the ends, you have, so here's your LA River floodplain. And at the ends, you have the river banks, which are just sloped things that rise up kind of to the main ground level. I just saw something flicker in the participants window. Did someone quickly have a hand up, or is that just my screen doing something weird? If you had a hand up, put it back up. Okay. Oh, I see it. Okay, I'm going to assume that was my screen. But does this general idea of, you have a channel and then a floodplain and then the riverbanks going to the ground above make sense? And this is right by the freeway. You've probably seen this. But yeah, this is your idealized river structure. So the thing about that channel, let me go back to the slide that went out of order. So it's still considered a stream, even if the water isn't always there. So like the Potomac River in DC it's what's called a permanent stream because there's always water in that. Like it never gets dry enough there for that to go away. And so we call that a permanent stream. But here in Southern California, it gets really dry a lot. And so sometimes there just isn't water in the river, which seems pretty normal to people in California, but people visiting from the East Coast think that's really weird. My parents make fun of that when they visit. But yeah, the Santa Ana River is still a river, even if there isn't necessarily water in it at any given time. You still have that channel in the middle, and then the kind of floodplain out to the sides. And then in this case, the bank has a freeway on it, but it goes up further and still has that structure. But that word for when there isn't water in it all the time is ephemeral. It's there and it's gone and it comes back and it's gone. But it still counts as a stream because of that structure like this, except, ideally with dirt and not concrete. So any questions about that structure?
Can you go back to the last slide, please?
To that one?
Yeah.
Yeah, what's up?
No, I just need to copy it real quick.
Okay. And again, don't worry too much if you miss something like during the lecture, because this is a one lecture topic, so these slides will go up immediately after we're done today also.
Okay, we're good. I just need to get the two, the permanent and ephemeral.
Yeah, so this is your general river structure. But where does this come from? Does anyone, obviously the LA River paving thing came from paving, but why did they make it this shape? Why do rivers make this shape? Or streams in general make this shape? Does anyone want to guess? Also, can you still hear me? Because there's a ton of sirens outside and I can barely hear myself. Okay, good. Okay, so let me ask this another way. So remember how when we were talking about the steps of the sedimentary process, the steps of making a clastic rock, your weathering, your erosion, your transportation, and your deposition. Do you remember what the main thing, there were a lot of ways we talked about doing that, but what was kind of the main force that did that? It's the same stuff that's in the river.
Water?
Yeah, water. So it's sometimes the thing that seems really obvious is totally the right answer. So when in doubt, just think about on the test too, just think about what just makes the most perfectly reasonable sense. The river is water. The water is probably doing some stuff. So it's totally okay to think of processes like that. And in fact, it's even better to think of processes like that than to think about just memorizing. But in this case, yeah, you don't mess with water. Water is extremely powerful. It can scour rocks into bits, and depending on how fast it's going, it can carry giant boulders pretty far. But on the other hand, even if it's not necessarily doing that, it's moving. It's gonna gouge out the ground that it's flowing over, right? Just think about even if you were ever a kid playing with the hose and you were just using it to or even just cleaning your car, and that water coming out of the hose is pushing the dirt away from your car or making a path through your yard or whatever. It's the same idea with a river. It's that flowing water is very powerful. It's why, again, these things are, they're involved in that weathering and erosion and transportation and deposition, all of those processes we've talked about the last few lectures. It's because flowing water is a really powerful thing. Flowing water, 6 inches of it can pick up a car. So it stands to reason that if it's hanging out in the same spot on the ground, it's probably going to dig itself in further and further. And so that's pretty much exactly what's going on, is it is digging that trench itself. And the reason for that is that water wants to flow downhill. I mean, well, the reason for that is partly that flowing water is powerful, as we just talked about. But the reason that it collects in the same spot, the reason that it tends to go and actually form these channels rather than just trickling all over the whole landscape, is that water flows downhill. And that, again, is like kind of the simplest thing to think about. But on the other hand, it controls so much. So if you can just remember that water flows downhill, you can also probably think of all the processes. You can probably work back out a lot of the stuff that we're about to talk about just from thinking about that. But yeah, not only does water flow downhill, it wants to be as downhill as possible. If you were to dump water on an uneven surface, it would find the place that was the most down compared to where else it was. It's never ever going to go up unless it's super duper pressurized. But let's say you pour it in a not super duper pressurized way. It's not going to ever go up, but faced with a like sort of downhill and an even more downhill, it's always going to pick the most downhill option. And so in that case, like when you say, let's say you have snow at the top of a mountain and it's melting and there's, a bunch of ways down that mountain, but one way is more down than the others. The water's going to go that way. At first, it might have a bunch of little branches and trickles and rivulets and tiny streams as it's trying to find its way to the most downhill spot. But eventually it's going to get there. Eventually, all of those smaller streams are going to coalesce into larger ones and larger ones until the main river, by the point you get to a large, wide river, it's in the spot that is the most downhill compared to like everywhere else. So, I mean, I wouldn't say, go and set up, I mean, if you wanted to like, if you're bored or looking for a way to distract yourself from the news tomorrow, like set up an experiment, just see what happens when you pour some water on something sloped. But in this case, really, because the ground is uneven, and especially in a place where you've got mountains, because you kind of need a slope for water to flow downhill, and the highest point on that slope is probably going to be some mountains, and mountains form in pretty cataclysmic tectonic ways. If you remember when we talked about like crashing tectonic plates into each other and making big mountains, and we'll talk even more about that in our metamorphic rocks unit. But yeah, you've got this really complex like crunching of rock, and it makes an uneven landscape, and water is going to find the easiest, most downhill way it can go. And once it finds it, especially by the time you've got a lot of water flowing, the more water you have, the easier time it's going to have just carving out its channel. Does that make sense? We're okay. I see some thumbs up. If it stops making sense, just let me know. But I'm going to keep going. So there are other ways water gets into streams. Like there's usually a lot of water in the ground that contributes to it from below. That's a whole other can of worms that we're not going to touch much in this class. Although it is relevant for the flood stuff later. But if you are interested in water in the ground or water on the surface, there are some other classes in our department that are all about that. We have a few people in our department who are specialists in water. But basically what you want to know is water is going to flow downhill and dig its own trench. It's going to do that by weathering and erosion and transportation. It's going to loosen things and move them from their sources and take them away and carve out that trench. But at the same time, when we talked about depositional environments last week, we talked a lot about fluvial environments. We talked about how streams also drop off the stuff they're carrying. And that's also why it doesn't just keep digging down and down and down until we get into some like bad movie territory of reaching unobtainium or whatever, which is, by the way, totally fake. But they keep dropping off sediment as well. So it eventually becomes a kind of self-sustaining thing. So it doesn't just carve infinitely down, because as much as it's moving sediment, it's also dropping it back off. So that's why we're talking about this in our section of the class about sedimentary rocks. Even though it's water, the sedimentary process would be a very, very different situation without water and without streams. So, slide. So this process can be pretty gentle. So this is the Columbia River Valley between Washington and Oregon. And here you can see this is kind of a wide, placid, I mean, it can get pretty rapidsy in certain places, but this spot is pretty wide, relatively gentle. You can see here's the channel, here's the floodplain. You can see the banks are kind of steep, but not like crazy. It's kind of a wide valley here. And this is, you've got a lot of flowing water over a lot of time. But by this point, this is fairly close to reaching the ocean here. It's not flowing at a really crazy speed. But this can also be a much more really intense process. So like that's how you get the Grand Canyon, right? So this is the Colorado River, and it has cut down through these thick layers of sedimentary rock. And some of this just has to do with it being, with the kind of stream it is, how it gets very high flow in the wet season and compared to lower flow in the dry season, whereas the Columbia is in the Pacific Northwest. It has a more consistent rainflow behavior. Some of it is also actually tectonic, in that the Grand Canyon, there was also some things about this rock rising up as the river was cutting down. But the point I make in this is that general river shape of having a channel and having a floodplain and then having banks depends a lot on where it is, on how fast it's flowing, on what kind of rock it's in, on what the rock around it is doing. But all of these things, this sort of gentler looking valley and the Grand freaking Canyon are all a testament to the power of water. So like Water Tribe, we're on it. Any general questions about that? About how, do you understand how just the idea of flowing water moving through a different kind of landscape, a different kind of tectonic setting can create either of these things? And honestly, the next time you're near a place with flowing water, just kind of look at the shape of the land around it. You'll probably, whether it's small or large, you're probably going to be able to start to recognize some of that channel, floodplain, bank shape, even with something pretty small. But yeah, I don't know why. Oh, the one on the gentle slide. So this, why are my slides being terrible today? This is the Columbia River between Washington and Oregon. And there are some parts of it that are pretty wild and intense and fast flowing and have very, very steep banks. This particular spot is kind of on the gentler side of it, because as we're going to talk about later today, kind of where you are along the river, whether you're closer to the origins, closer to the higher mountains versus closer to the ocean, does affect how fast it's moving and what kind of thing it's cutting through. But that's a few slides from now. Does that answer your question? Yeah. And actually, even if you compare to my background image, the Shenandoah River is even gentler. It's flowing through less of an intense landscape that is mostly going away by erosion rather than having active tectonics. But yeah. Okay, slides. So we were talking about how these things coalesce from lots of water trickling out of lots of different places, coming out of the high ground and finding the lower elevations and just flowing downhill as much as it can. And that's not something that just happens all at once. You don't just like, bam, get a big river out of nowhere. It comes from big rivers, big streams come from many smaller ones coming together and finding that most downhill path. And so those smaller streams that lead into the big ones are called tributaries. Is that a word that any of you have heard before? I think that's a word, yeah. So I see a yes. Yeah, I see more than one yes. Cool. Yeah, so just a tributary, a no. I mean, I'm going to explain it even if you all said yes because it's on the slide. But yeah, a tributary is just a smaller stream that feeds into a bigger one. It's a source of water for a larger stream. It's sort of water collecting out of a bunch of different pieces of high ground. And then eventually, so it might be like over here, this is the best path downhill. And over here, this is the best path downhill. And over here, this is the best path downhill. But then they all eventually reach this spot that is the best path downhill, and there's no other good path. So everything ends up here, and so on and so on. So basically, the more downhill something is, the more likely it's going to be that things are feeding into there. It's just this progressive thing of finding the most downhill way to go. And so again, so with this example on the left in the Los Angeles River coming out of the Santa Susana Mountains, there's a lot of ways you can go downhill. But then sloping down the San Fernando Valley, there's kind of only one most downhill way to go. And that's also coincidentally kind of why the freeway is there. It's easier to put a freeway in an existing path than to blast out something that doesn't exist. So the LA River kind of follows the 101 and then the 5. There's a whole lot to be like, I think that's more geography class, but like the geography of why freeways are following certain features is really very geologically influenced. Unfortunately, we don't have time for that, but if you take Geology 344, which I know I've mentioned before, my California geology class in the spring, yes, we'll talk a lot more about that. But yeah, basically tributaries are small streams that feed into the bigger streams. And so you can have tributaries of tributaries of tributaries of tributaries. The LA River is a pretty simple case. We're in a drier environment, but like looking at the Mississippi River, the tributaries go all the way over to Yellowstone. The Mississippi River is fed from Montana over to Maine, or I guess over to New York, not to Maine. Doesn't go all the way to Maine. The participants list was covering the edge of the map. But if you look at this, like the Mississippi River is huge. Have any of you actually like been to the Mississippi River? Okay, so what was that like since you said yes? Just like, can you compare that to the rivers? Yeah, fast flowing and enormous. Yeah, no, unfortunately. It's definitely worth seeing once travel is a thing again, once the virus rates in that part of the country are not ridiculous. But it is, if you only ever seen California rivers, it's going to blow your freaking mind. It is so large. But part of the reason is just so large is this is kind of the most downhill for the entire middle of the country. Like a lot of this land in, the Great Plains is relatively flat. It still has enough gentle slope, though, to carry things this way. Meanwhile, coming from further east, you have the Appalachian Mountains, and everything this way flows down to the most downhill in the middle, which is the Mississippi River. And so in this case, like a lot of these are really big rivers in their own right. The Ohio River, the Tennessee River, the Missouri River, these are big, but they just flow into something even larger. Because this is where downhill ends. And so all of these are tributaries. And so a tributary can have tributaries. You can it's fractal. It can go as small as you want and as big as it is. But the combination of all of the tributaries and its main trunk stream, and you might hear it called a trunk, and it sometimes is helpful to think of it kind of like a tree, where like you have little branches that go into bigger branches that go into bigger branches that eventually go into the trunk, which goes into the ground. Sometimes it can be helpful to think of this that way as well. But sort of the whole tree in the context of a river is called its watershed. So basically anything, if its water flows into the Mississippi eventually, it's part of the Mississippi watershed. If its water flows into the Los Angeles River eventually, it's the Los Angeles watershed. Does the river in my background connect to the Mississippi? It does not, because it is east of the Appalachians. So the Appalachian Mountains are here. And it actually kind of runs through the eastern or the eastern edge of there, flows into the Potomac here, which flows out into the Chesapeake and then the Atlantic. So this is, the Mississippi is like the largest, it's the biggest watershed of the country, but yeah. So does anyone have any questions about this? Cool. So what determines what goes into what watershed? So actually, just based on what I was just saying about the Shenandoah in my background not ending up in the Mississippi, even though it's kind of here, and the Ohio, which is not that far from it, yes, ending up in the Mississippi. What do you think might control what divides this up?
Mountains?
Yeah, mountains. Where is downhill? Where is the most downhill? So, why are my slides being terrible? Cool. So yeah, the thing that determines which way it's going to go is called a divide. So yeah, it divides up the watersheds. This is another extremely literal word. And so basically, from our standpoint of water wants to flow downhill, a divide is the uphillest uphill. Nothing is going to flow over the divide. If you're standing on a divide, if you're standing exactly straddling that line of the uphillest uphill and you have a glass of water in each hand and you pour that glass of water, one on one side of the divide and one on the other side, they're going to go to completely different places. So have you ever heard, who here has heard of the Great Divide? Or even if you haven't heard of it in the context of geology, have you ever heard of it in like a song or a poem or just anything? Yeah, you've heard of it. Does anyone know, do you know what that is?
The Rocky Mountains?
Yeah, so the Rocky Mountains are definitely, yeah, so that's where the Great Divide is. But do you know like what that, have you ever stopped to think about what that means? Yeah, like a lot of people who put it in a song super don't know what it is. Like a lot of songs, I've heard a lot of songs that mention the Great Divide as if it's something like literally pulling apart, like a rift. It is not a rift. It is kind of the opposite of a rift, because a rift are things are dropping down and stretching apart. The Great Divide is a watershed divide. It divides which way water flows because it's the toppest top of the highest high. And so, yeah, the Great Divide is here. It separates it's the Rocky Mountains, and it separates sort of the desert Southwest and Pacific Northwest from the center of the country, from all of the stuff that goes into the Mississippi or into the Gulf of Mexico. And so again, if you were to go to the top of the Great Divide and pour a glass of water on either side of it, water from one hand would end up in the Gulf of Mexico and the water from the other hand would end up in the Pacific, because there's just no other way it can go. And the reason that these are so definitive is, again, it is just the highest point. It's not just that there are, on either side of this, there are going to be different uphills and downhills. But it's ultimately like it says there's literally no way you can go. So like if you think about, let's say you're within one watershed or one drainage basin, which by the way, the word for, things divided up by divides are drainage basins. So you can have multiple watersheds in a drainage basin. So it's just kind of like a scale thing. But imagine like, let's say you were trying to go downtown, right? And you were on the 5. And the 5 was kind of awful. So you got off the 5 to take some other freeway. Let's say you were like, actually the 5 is terrible. So I'm gonna cut over on Sunland Road to the 210 to the 2 and go downtown. So you're still going downtown. You're taking a different route than the 5, but ultimately going to the place the 5 would have taken you. And that's kind of the idea of like smaller streams going around different uphills, but still ending up in the same downhill as you would in the same drainage basin or same watershed. But now imagine that you were like trying to do that and you somehow, let's say you were like, traffic's real terrible. You wanted to go downtown, but you somehow ended up on the 14 going towards the desert. And once you cross into the desert, you were definitely not getting downtown anymore. So it kind of splits the LA freeway system from all that stuff in the Central Valley or in the Mojave. So it's that same idea of like, there's certain inflection points where you're with one group of stuff or you're with other groups of stuff. Does that make sense? Hopefully you don't want to be that guy that's trying to go downtown and ends up on the 14 North. But any questions about divides or watersheds or drainage basins? And if you do find yourself questioning that later, just again, if you can remember that water flows downhill, you can just think about that process, just back out the process from that concept. So yeah, we are down here, part of this large drainage basin, even though we're in a pretty small watershed. Cool. So the size of the watershed does control how much water is in the stream, because you can only have as much water as in the stream as is coming from somewhere. Right. So the Mississippi River has an enormous volume of water in it because it has an enormous watershed, because it gets water from the entire center of North America. Whereas something like the LA River, it's partly dry because we're the desert. There's not a lot of rainfall in the mountains. So that's also part of it. But also just there's fewer streams coming out of it. So some of it is, the size of the watershed controls the volume of water. Is it a large watershed? Is it a small watershed? And also, is there a lot of rain or not? But some of it is also really important is, yeah, you might have a lot of water, but just because you have a lot of water doesn't necessarily mean that it's moving fast. So you can have a lot of water that's not moving. It's called a lake. But you can also have a small amount of water moving really, really fast. Like if you remember 2 lessons ago, yes, my sense of time is gone, when we talked about the difference between a mountain stream and a river, even though they're both channelized flowing water, that mountain stream is going super fast, even though it's kind of small, and that other river is going super slow, even though it's kind of big. You can have a lot of water moving slow and a little water moving fast. And both of those factors kind of change what that flow is going to do to the landscape, but also what kind of rocks you're going to get in there. So does that kind of check out with to you with what we talked about before? Does that still sound familiar, even though last week already feels like several weeks ago because election time? Cool. So I'm going to give you an equation. And I warned you that there was going to be an equation. It is a really simple equation. It has 2 things in it. So when we talk about, sort of what a stream can do, and some of it has to do with how much water is in it, and some of it has to do with how fast that water is flowing. And both of those things can be powerful in different ways and have different effects on the landscape. Sort of the combined effect of the amount of water involved and the speed that it's flowing is what we call the stream's discharge. How much water is getting discharged, how much water is going through. Like, when you say like you have been discharged from the hospital, which hopefully none of you have needed to be recently, but you say it's leaving. So this is the amount of water that is leaving the stream at that spot. And so when you calculate the discharge, you do it at a specific spot, because sometimes it can be different in different places along a stream. The slope can change. As it flows closer to the ocean, the slope might get less. As more tributaries come in, the volume might get larger. So it's the discharge of a stream is going to be different at different places. It's also going to be different at different points in time. But basically what it says is just, has basically to do with how much force is in that water, and it affects how much stuff that water can carry. And it's a really simple equation. So D discharge equals stream area, which is how wide and how deep, times how fast it's going. So it's just area times velocity, area times speed. And this equation is the only equation in this unit, and I would like you to memorize this one. I'm never going to make you memorize a chart, but I do want you to memorize this one because it has 2 things in it. I guess it could technically be 3 things because area is width times depth, but I do want you to know this. And after class today, there will be some practice problems with this up. So there will be some questions on the test based on this equation, and the practice problems, there's 5 of them, they're worth 1 point each, and you can do them over and over and over until you get them right. There's going to be some questions like that on the test. So yes, please know this equation, this simple multiplication equation. And again, for those of you not familiar with this kind of notation, this smaller letter is not a variable. It just says A sub C is how we'd say that is the stream area, and V sub A is the water velocity. Those are just the names people use for these. So this is one thing, and this is one thing. And so this is important because, again, both area, both stream area and stream velocity, water velocity, can affect what that stream does. The greater the discharge, whether it comes there from there being more water or from that water going faster, the larger the effect the stream can have on the landscape. The more it can carve down into the ground, the wider of an area it can flatten out into a floodplain, the larger sediment it can carry, and the more area it can put sediment into. Does that make sense? So then let me ask you this. Let's say you've got a stream that is 2 feet wide and 2 feet deep and flowing at 2 miles an hour. And let's say you got a stream that is 4 feet wide and 2 feet deep and flowing at 2 miles an hour. Which one is got a bigger discharge? The first one or the second one? I guess I can put those numbers in the chat box too. 2 feet wide, 2 feet deep, 2 miles per hour. And then 2 feet wide, or 4 feet wide, 2 feet deep, 2 miles per hour. So of those two things, I just put in the chat, which one's got a higher discharge? First one or the second one? Yeah, so the second one is correct. Why? Yeah, it's a larger area. It's bigger. So similarly, if I had said they're both 2 feet by 2 feet, and one of them was 4 miles an hour and one of them was 2 miles an hour, which one would have the greater discharge?
The one with 4 miles an hour?
Yeah, the faster one, exactly. So whichever one of these things that you make bigger, if all the other things are the same, the faster one is going to be more discharge. If everything else is the same, the larger area is going to be more discharge. But sometimes those things won't be the same, and you'll have to do the whole equation and figure it out. But in general, if I say they're the same size, the same area, but one is flowing on a steep slope and one is flowing on a gentle slope, which one do you think is going to be a larger discharge?
Can you repeat
The
that?
steeper one?
Oh,
Yeah. So I asked if you have two streams that are same area and one is flowing on a mountain and one is flowing on a gentle slope. And so the people who said the steeper slope, which was several people, are correct because it's going to flow downhill. It's going to go fast downhill. It kind of ties into what we talked about mass movements last time, how the steeper the slope, the more the gravity pulling down is going to pull it down the slope rather than just plunk it down on the ground. So yeah, this makes sense. And again, more discharge, the more stuff it can carry. So you okay with this? Again, these slides will be online. You will have access to this equation. So I'm going to move on after I drink some water, because talking about water makes you thirsty. How about that? Cool. Slides hate me today. Cool. So as I was saying, streams are going to transport different stuff based on what their discharge is. So that the higher the discharge, the more stuff it can carry, or the faster it can go. But in general, there's kind of 3 ways that streams are moving stuff based on their discharge. And so these hopefully sound familiar based on the vocabulary assignment you did. And if they don't sound familiar, maybe you forgot to do the vocabulary assignment, so go do it. You still get partial credit. But yeah, so you can have the, basically, streams are going to have a bunch of stuff. So even a very low discharge stream can have a lot of what's called dissolved load, which is just minerals that are suspended in solution. So if you remember, we talked a lot about dissolution when we were talking about weathering and when we were talking about how minerals are destroyed. When we also talked about minerals precipitating from solution, it's like they've got to get into a solution to begin with. So in this case, they're dissolving in the water. So the dissolved load is just sometimes, individual, like not even visible with the naked eye, like molecular level stuff sometimes, just floating in the water. And because that's so small, it doesn't need to be in very fast flowing or high volumes of water. So you can have pretty low discharge streams still transporting minerals in this way, even if they're moving too slowly to actually pick up a grain of sand. But as the discharge gets higher, you can have more and more transport. You can have what's called suspended load, which means that there's stuff in the water that is solid, that might be visible with the naked eye, but it's going in the water, it's floating, does not touch the bottom. And so these are usually still our small clasts. So if you remember our clast size chart, like you're still going to probably be talking about your silt and your sand steer. Silt and sand still here. But in this case, the water there needs to be enough water to pick up stuff. It needs to be going fast enough that it doesn't drop a piece of sand. Or maybe even some pebbles. But in general, a lot of streams, even your creeks and stuff, are probably going to still have this. But once you get into really high discharge, either large volumes of water or stuff that's moving fast, this starts to be able to bump along some pretty big stuff. And so in this case, like you're not very often are you going to have a flow of water capable of like lifting a boulder and carrying it through, but you can have water dragging these things along the bottom in what we call the bed load, because it's on the stream bed and it's just kind of dragging or bouncing. So there's a couple of ways that can happen. It can just roll or it can bounce. And so that fancy word for bouncing is called saltation. Of just class just sort of like bouncing along the ground, and like they'll bounce off a rock and then fall and bounce and fall and bounce, kind of crashing into each other. If you remember when we were talking about how the roundedness of a clast has a lot to do with how far it's traveling, this is a really good way to round out a clast real fast, is to just keep crashing them into each other on the base of a stream as it flows. So pretty much all streams are going to have dissolved stuff, but the higher the discharge, the more and more you're going to have of these other things. And it's also worth noting, though, that this also kind of has to do with where across a stream you are. Because even though that, that discharge equation is just kind of an average, it says at this point on the stream, this is the discharge. If you think about just the structure of that stream, how the channel is deepest in the middle and like it's shallower at the edges and on the floodplain, the water isn't necessarily going to be flowing at the same speed on every part of that stream, even at a given cross section. So the stuff in the middle of the channel is probably going to be going the fastest. So if you were to find like, you might expect rocks with larger clasts to form at the center of a stream. And then as you get into the flowing water of the edges, you're going to get smaller and smaller clasts because there's less water to carry them. So at the part where it's still underwater, you might get finer clasts. But then if you think about a flood, which we're going to talk about real soon, sometimes floods are a lot of water coming all at once, and they can carry bigger rocks than normally. And so they're going to drop those off, they're just going to be carrying them. But then when the flood recedes, those big clasts that the flood was holding are going to stop and end up on the edges of the river. So you get kind of these different patterns of stuff forming at different parts of a river. So that's why you might get breccias or conglomerates at the center and on the banks, but at the sort of edges of the flow, you might only find sandstones. So does that make sense? Does that jive with last week? Do you see why I saved this for this week as opposed to trying to fit this into that other lecture? Cool. I'm going to take that as no objections. So if you think of stuff, just type them. So yeah, so for all that streams are transporting things based on their discharge, they're also depositing them based on their discharge. This is all of the steps of the sedimentary process are happening in the streams. And so basically the speed, the amount of discharge also, and especially the speed, but also the amount of discharge affects what gets dropped. And so generally the steeper of a slope you're on, the faster the water is going and you're going to have a better time carrying boulders. But also the further these things travel, the more they get broken down into smaller clasts. So you're going to find bigger stuff at the top in the mountains and smaller stuff down at the base. So if you remember when we were talking about deltas last week, most of that is silt and clay because by that point, things are pretty flat. They're not going pretty fast. Even though there's a lot of water, the discharge can still be fairly low because it's slow. And all of this stuff just kind of sifts out, and all of the bigger stuff dropped out sooner. So this is just kind of what's left. Does that make sense? You would have some very, if you could carry boulders all the way down, deltas would not really look like what they look like. You wouldn't have this gentle sort of fan out, or even alluvial fans would look fairly different. But yeah, any questions about discharge? Cool. And again, you can do that assignment, the practice problems, as many times as you want until you get them right and until you memorize the equation. Yeah. Are these boulders the size of large rocks? You all love the small boulder the size of a large boulder, the large boulder the size of a small boulder. These boulders can be large or small rocks. I know you sent that to me privately, but if you're gonna meme, I'm gonna meme. Anyway, let's move on. Or if that wasn't a meme, then I apologize and I'll answer that later. But yeah, moving on. So that was normal river stuff, normal stream stuff. Most of the times it is for the memes. Okay. Most of the time streams aren't flooded. If they were, then their channel would just be larger and they would equilibrate until they weren't a flood anymore. You would just have a bigger stream. You have streams of different sizes. The definition of a flood specifically is that the volume of water in the stream is bigger than the channel. And if that consistently happens, the channel will eventually become bigger. But for the most part, a river is just going to be hanging out in its channel. And when something happens to allow it out, then it's a flood. And so if you hear the phrase flood stage ever, that's actually like when the channel is completely full. And then flood, at that point, it's still in the channel, but like one more drop of water is going to make it go splashing out. I mean, if you hear the phrase flood crest, that is the peak, the highest depth of water that it gets. And that's measured not from the base of the channel, but from the top of the channel, from the flood stage. So does that make sense? So streams are supposed to flood. So even though, when I say flood, do you think of that as like scary? Like what is your sort of immediate connotation when I say flood? Wait, can I go back for a second? Yeah. So while you're writing that down, what is your immediate, just anyone, your immediate thing that you think of? Like water rising, lots of fast moving water with debris. Yeah. So generally, if I were to, would you categorize a flood as a natural disaster? Is very often, like if you were to take a class called natural disasters, there would totally be stuff about floods. And definitely, if you're a city planner, yeah, that's absolutely a natural disaster. But the important thing the thing that makes it a disaster is when it screws up stuff for people. So yes, it is very anthropocentric of us. I think I made up a word. But floods are a natural process. This is a thing that is totally supposed to happen. And it's only disastrous when we get in the way. But just if you remember our stream morphology, our shape of a stream. So this one is a nice kind of wavery stream, not a snake. But we call these meanders. Don't really have time to get into why they form in this, but I guess, yeah, it's a snake on a plane. If anyone remembers that movie. But if you think about this, like you have the channel, but then you have this wide floodplain on either side of it. And you wouldn't get that if streams didn't flood. If flooding weren't a totally normal, natural thing, you'd just have the channel and then the banks, and that would be it. The fact that a floodplain exists means that water flowing has created that shape, and that it happens regularly, and that it's totally natural. This is totally supposed to happen. And so if anyone remembers, like taking your world history classes, talking about ancient Egypt, or talking about Mesopotamia, which literally means between two rivers. So Egypt is super the desert. Mesopotamia is, it's Iran. It's super the desert. The reason those places were able to be cradles of major advanced human civilizations is not because they needed less water than the rest of us. It's because rivers flood, because there was enough discharge in the Nile or in the Tigris and the Euphrates to not just be wet, but also to flood and deposit sediment, which could be used for farming. That's this rich Nile silt. The whole agricultural history of ancient Egypt depends on the silt of the Nile coming out of the riverbank into the floodplain and being something that they could farm. If you read Egyptian mythology, it's like super all about that. Lots of river and flood and agriculture gods, very much a seasonal thing. Yeah, this is, this floodplain is here. So you can see the freaking desert that is most of Egypt. And you see the channel of the Nile weaving its way through here. But this very wide green band, so 10 kilometers, it's like 7.5 miles wide of floodplain that is green and rich and fertile because this floods every year. It's supposed to happen. It's what rivers do. Or again, if we go closer to home, yeah, there's a floodplain. There's a flood in the floodplain. So see here, this is the channel. It's channelized, but here the water has spilled out over the concrete channel into the concrete floodplain. It's a flood. This is natural. This is supposed to happen. Just sometimes you get more water and it's got to go somewhere. So does that make sense? So like I was saying, they only become a disaster either when the stream gets too big for its floodplain, which sometimes happens, or when people build stuff in the floodplain, which, I mean, part of the reason this is channelized is to avoid problems like that. But you can see, let's say there were a situation where the LA River flooded so much it got out of the floodplain, like rip the 5, right? And actually, there were instances of that happening in the 60s. I forget if I put those, I think those pictures are still in this PowerPoint, but if they're not, I can pull them up after class if people are interested. I think they're still in here though. But yeah, floods are only disasters when there's like really a ludicrous amount of water that gets out of the floodplain or when people are in the way of the floodplain. Just like technically an earthquake isn't a disaster unless you build stuff in a place that gets knocked down. A volcano isn't a disaster if no one is there to get pyroclastic flowed. A lot of what we call a disaster just means that we, as our clumsy human selves, got in the way. But anyway, we still do kind of talk, but because we are here, floods are very much something that are disastrous, and there's a whole lot of infrastructure and ways to mitigate that. And honestly, that could be a whole other lecture that we unfortunately don't have time for in this class. But yeah, so floods in general, too much water for the channel, too much water for the floodplain sometimes. But within that, there are 3 major categories of floods. There are 3 main ways this can happen. So one is, remember how I just said that the ground can have water in it? The groundwater is a thing. It's not a thing we encounter too much here because we're basically the desert, but groundwater is a thing. And so the first kind of flood happens when the ground has so much water in it already that it just can't hold any more water. It is completely full to capacity and anything else is just going to pile up on top. And so we call that a slow onset flood because it takes a long time. It requires a lot of rain over a long period of time until the riverbeds get full and the floodplains get full and the groundwater gets full and the water just keeps piling up and piling up and piling up and piling up. And so that's a slow onset flood. It takes a while. Your book calls that a seasonal flood because it generally takes a whole season worth of rain to do. But I actually really hate that term because really all kinds of, not all, catastrophic floods do whatever the heck they want. But most floods have a season that they occur in. They occur in the season with the rain. So I prefer the term regional flood, and a lot of other sources do too, for a slow onset flood. Because it occurs over a large area. It generally requires that there being a lot of rain over a large portion of the watershed, such that it piles up and none of the tributaries can get it away in time, and all of the ground gets too saturated. And I will have more slides about all 3 of these in a minute, so I'm going to introduce these and come back to them. But yeah, so I'm going to say regional flood. Your book will say seasonal flood. They mean the same thing. On your test, I will say regional flood because I think seasonal It's kind of a dumb name because fast onset floods, which we're going to talk about next, are also kind of seasonal. So a fast onset flood is most of what we get around here. So you ever notice like literally every time we get a rainstorm, the thing is like flash flood watch? Does that sound familiar? Flash flood warning even? Yeah, so I see yes. If you haven't, so lots of yeses, but if you somehow not noticed that, just pay attention the next time it rains. The weather forecast will say that because it just always does, because the ground here is so dry. So a flash flood or a fast onset flood is exactly the opposite. It's when the ground is super, super dry and so much water accumulates so quickly that the ground can't absorb it fast enough. And so you go from 0 to raging torrent sometimes in seconds. But at the same time, those also go away faster. A slow onset flood can take a long time to start, but a long time to finish, just because there's so much water involved. But a fast onset flood is usually not a huge volume of water. It's just too much it's just coming down faster than the ground can handle it. And so once the ground is then able to absorb that, the flood kind of stops. So these are, and again, here in Southern California, they happen in the winter. They are seasonal because that's when it rains. I mean, they can happen in the summer if it rains in the summer, but since when does it rain in the summer these days? Climate change is real. But basically, flash flood, I mean, the name flash tells you it's fast. Yeah, so, and then the third kind of flood isn't seasonal. It's just if something breaks and lets the water out. So the third kind of flood is called a catastrophic flood. And so that name, of course, is very dire. It makes you think this is a catastrophe, everything is terrible. But technically, this does not inherently have to be a disaster. If something like this happens in the middle of nowhere where there's no stuff in the way, yeah, you're going to have a massive change to the landscape caused by a huge volume of water flowing across it. But if there's nothing in the way, it's just going to happen. The reason it's called catastrophic is that it's kind of all at once. It's instantaneous. It's that something fails and the water gets out. It can be a geologic structure, like an ice block, or like a landslide can move and let a river out. Or it can be a man-made structure, like a dam or a levee. But just if something that is meant to hold water back or has been holding water back fails, and the water goes, then it's a catastrophic flood. So we're going to go through all three of these in more detail, but does anyone have any questions about these before I do that? And I have videos of some of them, mostly fast ones. Cool. All right, so let's talk about regional floods first. So slow onset or regional flooding. It takes a while, but it lasts a long time, and it's usually a pretty large area. And this is just it rains and 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 it rains some more, and the river gets full, and then it goes out. So here's some examples from the 90s in the Mississippi watershed. So here you have the Illinois River, which is a large river, the Mississippi River, the Missouri River, which is a large river. This is kind of where they all come together. And this picture on the left from August of 91 is normal. Like this is, I mean, it's summer, so it's wet. The wet season in this part of the country is summer. And so, yeah, it's green, it's wet, but, you know, the rivers have water in them. These are not ephemeral, these are permanent. But, you know, they're pretty well channelized. You can see here's the stream and here's the stream, and you can see some different little strands of it, but it's kind of in place. I mean, and this stuff, by the way, some of it's agriculture, but some of this is populated. Because generally where you have rivers coming together, it's a great place for trade, which is a great place to put a city, which is a problem when it floods. So if you look at this picture on the right, this is the exact same area in August of 93, and I don't think I need to tell you that it's different. So that is not, it's not different coloring, it is just a different photo, and all of that dark stuff is water. So this is a really severe regional flood, and it really is regional because you can see this scale bar, 5 kilometers, it's 3.1 miles. So this is like 5 miles across of water. And, you know, the people living here are having a bad time of it. The people living at these confluences are having a really bad time because this is an enormous amount of water coming together. This is a regional flood. And so this is what it looks like from the air, because you can see these from the air. But it's a lot scarier from the ground. You get situations like this, where this isn't from any one like hurricane or anything. This is just rainstorm after rainstorm after rainstorm, filling up until it just overflows the river, and just these are houses that are filled up to the roof. This is in Illinois. You know, this bridge is supposed to cross this river. This bridge is not crossing this river. You know, this is a thing where it was supposed to come down gently, and it just doesn't, because the water level is so high. And if you were to go into these streets over here, there would be water in these streets. These are the kind of situations. So this is in Missouri, Kansas City, Missouri. There's the state capital, not Kansas City, Jefferson is the state capital. But this is, you can see, there's the river. This is supposed to be downtown. There's the state capital. There's a problem. This is the kind of thing, like, and this happens fairly often. And so if you're ever seeing pictures of people in like the Great Plains and in the Midwest and sort of in the South riding boats through the streets, it's because of something like this. And you can see why this is a problem. This takes a long time to drain just because there is so much water. People can usually tell it's going to come because there's just so much water. But at the same time, it can take months, you know, weeks or even months before this goes back down below flood level. A regional flood, really nasty. Any questions about that? Cool. So then flash flooding is kind of the opposite. Again, it's that idea where you get a lot of water at once and the ground can't accommodate it, and you go from zero to whitewater rapid in super fast, but then it doesn't last very long. And so this is, so this is Mill Creek in the San Bernardino Mountains in, I think, January of last year. And this is a flash flood.
We are here in Mill Creek, Southern California. And this right here is some flooding going on. This is Mill Creek, comes out of Forest Falls. And
Forest Falls is the place I showed you with the debris flows last time.
Is Kuiper Ridge. Kuiper Ridge got 10 inches of rain the past 24 hours, actually more. And on top of the snow they had up here, all that rain's washing down the snow and causing this crazy melt, this crazy runoff. This is a major flash flooding, and this right here is they're saying it's like a 50-year flood. Usually this whole area is dry in the summertime. And I've only seen it once before when it's this wide across.
So I'm going to pause that. But this whole video will be on Canvas when I upload this. Oh yeah, that comment, the thing about the tour ride at Universal Studios with the flash flood. So I went on that and was disappointed with the earthquake in that. But the way they had the flash flood, where it really is just a whole lot of water comes in at once, like honestly, that's not wrong. That's basically what happens. But when stuff like this happens in your backyard of the studio, like they've seen it. But yeah, again, looking at this thing really is dry most of the time. But you can see how on the sides of this, there's some really big cobbles and really little boulders, small boulders the size of small boulders. Things like this get moved, not by this being ephemeral, not by this trickling most of the time, but in flash floods like this. Yeah, and so luckily this one is staying in the stream. And often like these will stay in existing channels, but sometimes they don't, and that's when it's worse. But yeah, so some other examples of how quickly these can happen. So this is the Santa Ana River near Riverside. This is something that one of my professors took in, I think, the 80s or early 90s, and then kept using it in his class. So this is the Santa Ana River in winter most of the time. It's a little wet, but this was a wet winter. And very quickly you start to see just the stream bed filling with flowing water. But then, and he started backing up after that. And then eventually it gets to just a full on, like, you would not, like this, you might go, I don't know if that's really a river, except it is because you got the banks, you've got the shape of the river. But then this is like, uh-oh. And this is like, yeah, that's a river. And so a lot of the rivers in Southern California actually kind of work this way. But this is a flash flood. And, so this is going to flow really intently for, sometimes a few minutes, sometimes a few hours, maybe even a day or two. But then it just kind of goes back to what it was. And so And this can happen on a smaller scale. So if you remember, I showed you my street that I lived on that had the sinkhole last time. So this is the same street. It's coming out of these mountains. This is called Big Springs Road. You would have thought they would have known it would be a flooding and sinkhole hazard with a name like that. So this was also a flash flood. It was a little bit cursed. But yeah, I lived in this building and sometimes it was hard to, this street, I can tell about all of the issues of living on that street later. But you can see here, this is super steep and this came out of the mountains and coursed down and kind of flash flooded its way into, there is a drain here. The drain was supposed to pull that water under the street and then have it flow under the street, but that's how the sinkhole happened. So flash flooding can be damaging, can happen in places that aren't obviously rivers, can happen in places that have infrastructure on them. And it can do a lot of damage. So this is further up the hill, like if you walk up the mountain from that. So down here, the water level's already gone down, but can you see just how much stuff is caught in this fence? That shows that the water level was up this high, that the water level had maybe even overtopped this fence and just all of this debris that it was carrying got stuck in the chain links. Flash floods are quick, but it's even a little bit of water moving very quickly can cause a lot of damage. And so they're dangerous. I definitely would not choose to live in a flash flood zone again, but I didn't know this much when I moved onto that street. Any questions about that, about flash floods? Let me ask you this. Looking at these precipitation charts, so these are rain charts, one for LA and one for New Orleans. So this is the month of the year compared to the amount of rain per year. And so looking at this, which of these places do you think is more likely to have regional flooding versus flash flooding? Pretending you didn't live in one of these and didn't already know the answer. I should have picked a different city. Yeah, so New Orleans is more likely to have regional flooding. Why? So anyone want to guess why New Orleans has regional floods and not flash floods? Yeah, it has more rain, like all the time, especially if you compare, the maximum here for LA is like 4 inches. Here it's 7 in New Orleans. They get so much more rain that the ground is always wet. And so it's much more likely to have a situation where the water piles up. Whereas here, we're super dry all the time. And so this is a case where it's just like the ground goes, what is this? And there's a flash flood. So yeah. So the last kind of flood, regional floods can still happen in dry cases. This is what I was talking about. So sometimes if you have an unusually wet year, like in 1938 in LA, you can get a regional flood. The LA River did the thing. The LA River and the surrounding thing built up so much water that downtown LA, this is downtown LA, we used to have public transit in the 80s, or not the 80s, in the 30s, before freeways. Imagine that. You used to be able to take a streetcar from San Bernardino to Santa Barbara, and then they put in the freeways. So if you've ever seen Who Framed Roger Rabbit, like that part of the story is real. But anyway, yeah, the LA River had a regional flood in the 30s. And you can see here, it is out of its floodplain. The 5, if it had existed then, would have been super underwater. And that's actually partly why they built the concrete thing, is to avoid this problem. But eventually, anytime it's not just limited to certain places. So though flash floods are more common here, this can happen. But yeah, I'll come back to this. You might have heard the guy say 50-year flood in that video. And so the term 50-year flood, it's a recurrence thing, but it's not like an earthquake recurrence where you might go, we expect this fault to have an earthquake every 150 years or so-ish. We'll talk more about that later, but it's a probability. So it's like the percentage likelihood per year that a flood of that size will happen. So this is convoluted. I'm not going to ask you terribly much about this on the test, so don't worry too much. You might have like one question about this. But basically, if you hear the phrase 100-year flood, that means that the flood has a 1% chance of happening in that year. Of course, you could have two 100-year floods in a row in 2 different years because it's just a 1% chance because a percent is 1 in 100. So a 50-year flood is 1 in 50. It's a 2% chance per year and so on. So does that make sense? Don't worry about this too much. Just know that like when we talk about like a volcano erupts on average of every this many years, or an earthquake erupts on happens on average of every this many years, that's really based on a physical process of accumulation and release. Whereas this is just how much rain did you get? So it's a percentage rather than a buildup. Yeah. But the last kind of flood, real quick, it's not going to take that long, is called a catastrophic flood. Happens very quickly where something just fails. So this is in northern Japan in the 2011 earthquake and tsunami. And in this case, this thing here is a flood wall. It's supposed to keep the ocean in, and it didn't, because this tsunami was just much larger than they could have ever expected. And so this counts as a catastrophic flood because all of this water is just like, screw you and your flood preparedness, I'm gonna rampage. And definitely the severity and duration depend on the details. So in this case, like this was very bad because it was a whole lot of water moving very quickly, but it didn't last very long just because of how tsunamis work. We'll talk more about tsunamis later in the earthquake section. But sometimes they can be a much larger scale than this, and sometimes they can last longer or be faster. And these can be natural. So like an example of a natural one was about somewhere in this 15 to 17,000 years ago across the Pacific Northwest. And so that was when glaciers were a lot further south, and there was this thing called the Cordilleran ice sheet that was blocking a river in Montana. And so because this was blocking a river, the river couldn't flow to the ocean, and it made this thing called Lake Missoula, which was just a huge lake blocked up behind a glacier. But glaciers are made of ice. We're going to talk about glaciers all day on Wednesday. But they are made of ice, and ice can crack, especially if you repeatedly whack it with a lot of water. And so at some point, just that ice dam failed. The force of the water in Lake Missoula, just the volume of it and the flow down from the Rockies became so much that that just cracked the ice sheet. And the whole volume of this lake, which is the size of a considerable part of Montana, spilled out downhill all the way to the Pacific and just scoured the landscape. All of this used to be more forested, or at least more than it is now, but just this flow of a massive amount of water, the volume of like some states in New England, flowing across all of Eastern Oregon and Washington, and then through the Columbia and out to the Pacific, made this thing called the channeled scablands. And so all of these features are just from where tons of water flowed across and scoured the landscape out, making these kind of chunks of like remaining scabs of remaining stuff on the land. So that's a thing that can happen in nature, but more often these days, catastrophic floods happen due to people screwing up. And so a very pertinent example of very close to home was the St. Francis Dam disaster in 1927. And this is up in San Francisco Canyon, kind of up near the Grapevine. And this was part of the system bringing water into LA from Eastern California. And basically they had this dam here for a while, and the people who built it were like, well, that crack that you pointed out is probably nothing. The crack that they pointed out was not nothing. And so like I think it was less than a year after this thing was finished. It was a very small amount of time after the dam was finished. And people, you might notice this dark spot where it's kind of wet. It failed. This water just cracked and failed. And so this is where the dam was, and this was the most downhill. And so on the evening of March 12th, 1928, this huge volume of water came crashing through all the way from here out to the Pacific, through many communities, through Fillmore, Santa Paula, Ventura, out to the ocean. And this killed, I think it was more people than the Northridge earthquake, I think. Killed several dozen people, and just completely, like, this is where the dam used to be. The dam is gone. And it just caused wreckage like this along its entire path. And some people were able to get out of the way closer to the ocean, but the people closest to the canyons just didn't get any time and were just blasted out of their homes, just scoured through the edges of the valley in one of the worst dam failures of sort of modern history. So that's catastrophic flood. They can be caused by people, they can be caused by nature, but luckily they're the least common. And with that, we are done. So if you don't have any questions, well, I mean, even if you do have questions, you can go. If you do have questions, I'll hang out and answer them. don't forget to do the quick quiz, the next vocab, and learn that equation. And try not to doom scroll too much tomorrow. I will upload this slideshow immediately after this lecture is done. And cool. Yeah.
Thank you.
Okay,
Professor.
yeah. So someone just sent me a link. The St. Francis Dam collapse killed 431 people, whereas the Northridge earthquake only killed 60. But yeah. So with that, I will hang out if you have any more questions, and if not, I will. I'll hang out until you're all gone, and I will see you Wednesday.
Bye, Professor. Thank you.
See ya. Thanks. Are the rest of you, do you have questions, or are you just there? I'm going to end the lecture, and if you do have questions, just don't hesitate to send me an email.